Testing on YouTube. Testing on YouTube. Testing on YouTube. Testing on YouTube. I have to eat this ad real quick. All right, now we go. Testing on YouTube. Live on YouTube. How's it going, Mark B? All right, perfect. I'm just going to wait for X. How's it going, Lil KM? And Sarah. All right, I think we're live on X as well. Let's double check that it works on X. Something went wrong. Try again later. Try again later. Refresh, refresh, refresh. Broadcast not available. Try again. Oh, all right, there we go. Testing on X. How's it going, Tim and Mark B? Yeah, we're going to be talking about robots today. And yeah, you did make the start of the stream, Tim. Congrats. Okay, testing on X. It works. Perfect. All right. Wait up. I have audio coming out of something. Okay. I think we're good. How's it going, Sagar? Let's get this started. We have the Horn of Gondor again today, so we're going to blow this. All right. Hopefully, Rohan will come to aid. Today's stream is going to be called Real2Sim2Real. So Real2Sim2Real is kind of a new robotics technique that I see popping up everywhere here, and it's kind of a take on Sim2Real, which has been around for a while, but now we got Real2Sim2Real. So the majority of this stream is I really wanted to focus on this paper here. This is the ASAP paper, Aligning Simulation and Real-World Physics for Learning Agile Humanoid Whole Body Skills. This paper exploded this week. Obviously, being a Jim fan, and this paper being NVIDIA and Carnegie Mellon University, I felt like I had to do it. So a little bit of a return to kind of the more classic stream style. I'm just going to be going through the paper and a couple other related papers that came out this week, and then using it as an opportunity to talk about robotics and where it's going and whether this whole Real2Sim2Real is maybe what we've been hoping to do. But post-grad, I studied in Sim2Real. Pretty cool. Yeah, Sim2Real is kind of usually what people did, but these techniques are pretty good. And I'm actually going to start with this paper here. So, Improving Vision Language Action Models with Online Reinforcement Learning, 28th of January 2025. And if you look at the associations here, you got Shanghai Qizhi Institute, you got UC Berkeley, you got Tsinghua. Okay, so in this paper, they take large vision language models, or VLMs, and turn them using SFT, or supervised fine-tuning, into VLAs, or vision language action models, right? So VLAs, and you might have seen this pop up this week as well in regards to this. So Pi Zero, which is an open source vision language action model that was released by Physical Intelligence, which is a kind of a hot new robotics startup, but they also use the same terminology, this idea of a vision language action model, right? So a VLM processes and generates multimodal representations, right? Multimodal can refer to any kind of modality, but in this case, VLMs is specifically language and images. And then VLAs extend this by incorporating actions and observation tokens, right? So a state token and the state or the observation, similar kind of stuff, right? Observation might be not as clear as the state. The state might be, for example, the actual robot joint angles, right? Versus the observation might just be like the vision information that it's seeing. Action tokens are going to be kind of things like motor command sequences, right? And there aren't like super precise definitions for these, right? Things like state, observation, action, those can vary wildly depending on what robot you're using. Are you using it in sim? Is it a real robot? And so on. Okay, but back to this paper. So they take these vision language models or vision language action models, and they improve on them via reinforcement learning. Okay, so this picture here kind of shows you how what we're doing with the kind of curriculum or pipelines for these reinforcement learning vision language action models is very similar to what we're doing with chatbots. So the same way you can take a pre-trained large language model, in this case a pre-trained vision language model, which is in itself not even a single thing, right? Most vision language action models, the way that they're actually trained is they start with a large language model, which has been pre-trained, and then they also have a vision encoder, which has been pre-trained separately, and then they kind of glue them together and then train a little adapter between those, and that becomes the vision language model. So even the vision language model itself is kind of this Frankenstein, kind of like gluing together of a large language model and then a vision encoder. But let's say you start with a pre-trained vision language model. Then what you could do is fine-tune it on a robotics data set, right? So it at least kind of starts to input and output the things that you want in your observation and action space. And then once you have that, then you can use RL to just tune it a little bit more, right? And that's what they're doing. And here you can see how that's analogous to the idea of taking pre-trained LLM, then SFTing it on these kind of instruction fine-tuning, this is often called, right? Where you have these kind of like data sets of just fake conversations. You supervise fine-tune on that, and then you add a little bit of RL at the very end, right? The cherry on top, the RL from human feedback. Okay. How's it going, Julien, Majetti, and Dan? Apple also drops their robotics. Yeah, I actually have it pulled up. So at the very end, I do have this Apple paper, Elegant, Expressive and Functional Movement Design for Non-Anthropomorphic Robot. This is a rare Apple paper, Apple robotics paper, but it's pretty cool. I saved it for the end because I think I'm like slowly leading up to this Real2Sim2Real and kind of where it leads to robotics at the end there. That's why I wanted to start with this one. But here in this picture, right, you can see steps versus success rate. So here's steps, how long they're going to be training in these reinforcement learning environments. If you just take a vision language action model, I don't really know exactly what direct PPO here means. It basically means proximal policy optimization, which is a type of RL, but I don't know whether that means that they're basically using the same exact architecture and then just starting from scratch. But here they're comparing, obviously, the thickness of this represents the kind of variance. So sometimes you'll actually just use PPO and it'll actually start getting a high success rate, right? So the most successful run that they had was kind of this upper boundary. And you can see that it kind of gets a little bit of success, maybe 50% success, but then kind of like levels out. But then you can also have runs that are the same exact architecture, same exact everything, just a slightly different random seed, and it just goes nowhere. It actually becomes worse over time. But really what they're trying to convince you of here is that their two-stage approach where you first SFT and then do all, RL is better than just RL directly, right? RL from scratch. Okay, I think what else do I have in this paper that I want to show? Yeah, this right here. So our VLA, Vision Language Action Model, comprised a pre-trained VLM backbone. So this is the VLM, this pre-trained VLM. And again, that's also itself the product of a kind of multi-part training process where first you train the image encoder, then you train then you have the language model trained separately, and you kind of glue them together and then do this similar kind of things where you're freezing parts of it, pushing gradients, unfreezing it, and so on. But here they have the pre-trained VLM and then the lightweight action head, right? So the head just refers to that. It's at the end of the neural net. It's kind of at the head, at the very high end, right? At the top of the layers. And it's just a simple multi-layer perceptron that outputs the actual actions that you're going to execute on the robot, right? Where the actions are going to be maybe the positions of the joints that you want to head to. We iterate between exploration and supervised learning stages to effectively improve the VLA model. So there's an iterative reinforcement learning component here, right? So it's not like they're just doing supervised learning and then RL. They kind of RL, then a little bit of supervised learning, a little bit of RL, then a little bit of supervised learning. So it's almost like having two different components in your loss function, but rather than having two different objectives that you're pursuing simultaneously with some kind of hyperparameter in between them that trades them off. In this case, you're kind of alternating the training pipelines, right? So you're like feeding batches of this type of thing and then feeding batches of this type of thing. The VLM is frozen in the exploration stage to stabilize training and trainable in the supervised learning stage. Okay. So you can see here the robot is receiving the image, which has been tokenized into a sequence of vision tokens. And this is often where the VLM has to be kind of glued together, right? Is in order to take the stuff that comes out of that image encoder and turn it into tokens that can be understood by the large language model before it is called a VLM. And then you have the actual instruction, which is written in plain English, right? These just standard English text tokens. All right. You feed those into the VLM, outputs a sequence of tokens. Those tokens are used to into this MLP, which then outputs the action. Okay. What do we have here? VLM, action head. You see how they're alternating. They're not letting gradients flow into the VLM during the RL. And part of this is because if you let the gradients flow from the RL into the VLM, you're going to start messing up the VLM, right? You don't want this VLM to kind of start overfitting and catastrophically forget all the pre-training that it did before. You want to keep it frozen so that it doesn't lose that intelligence that it has, right? That kind of like general intelligence that you want out of your VLM. So you only push gradients into this action head, and then when you actually do the supervised learning, then you can push gradients into the VLM. Okay. And I think one last thing I wanted to show in this paper is this right here. So this is the reinforcement learning process in new tasks. You can see they're comparing unfreezing the VLM versus freezing the VLM and then learning from scratch. So this is basically, we just have the same architecture, but we're going to initialize it, and then we're just going to push gradients into it directly from PPO and RL, right? And you can see the learning from scratch. It'll learn how to do button pressing. So in button pressing, that's super easy kind of robotics task. It's similar to like picking, right? In a pick and place, where all you need to do is just move towards the object, right? So like that's probably the easiest reinforcement learning task to learn. So learning that from scratch probably makes a ton of sense that you can actually do that from scratch. But these other ones, you can see that trying to learn from them from scratch, these green lines are absolutely terrible. They don't actually learn, right? With these more complicated tasks like door opening, window opening, and so on. But the difference here between an unfrozen VLM and a frozen VLM, right? If you unfreeze the VLM, you see how just this quickly just becomes terrible, right? Because even though you're pushing gradients into these parameters, which means that on paper, those parameters should get better over time at this task that you're doing, right? There's so much pre-trained knowledge in that VLM that you're overwriting it with a relatively low quality, low amount of data, and that's why the performance drops here, right? This unfrozen versus frozen. Okay. Now let's go to this paper. Reconciling Reality Through Simulation, a Real2Sim approach for robust manipulation. This came out 24th November 2024, so a little bit older. And I actually used the OpenAI deep research to find this paper. I was kind of prompting it for the stream, and I was like, can you find me other Real2Sim2Real? And it found this paper for me, so that's how I found this paper. But in this paper, imitation learning methods need significant human supervision to learn policies. So imitation learning is effectively this right here, right? SFT on robotic data set, right? So imitation learning is whenever you have usually a data set of trajectories that a human has collected, right? So a human kind of teleoperated the robot and picked up this block 20 times, right? That is a small data set, and you can effectively SFT on that small data set, and that's called imitation learning. Another name for it, it's often called behavior cloning because you're cloning the human behavior, but it's effectively just supervised learning on some human collected data set. Reinforcement learning, on the other hand, explores the environment autonomously, right? This is the core difference between RL and SFT. In RL, you are actually interacting with some kind of environment and then collecting experience, and then that experience that you collect is used to push the gradient. So the data set isn't coming from an oracle human, it's coming from an actual environment. It's coming from the environment. But that's why reinforcement learning is very sample inefficient and very difficult to train, because you don't really know the quality of the data set that you're going to get from this kind of autonomous exploration, right? It could be that the robot just sits there and just hits the wall, it just like bangs its head against the wall 500 times, and you're not really going to push any useful gradients or learn anything useful from that. So it can be tricky to get the type of exploration that you need in order to actually collect the data set that you can then push into the model and then actually get some useful behavior. So in this paper, Real2, which is, I guess, their name for their thing, is real-world imitation learning policies via reinforcement learning in digital twin simulation environments constructed on the fly from small amounts of real-world data. So they call this Real2Sim2Real. And then they have a novel inverse distillation procedure for bringing real-world demonstrations into simulated environments. Okay, but what exactly is this pipeline? And let's go here. So they first start with this. This is the first step. 3D reconstruction of the environment, right? So they start scanning the environment with something like Polycam. Okay, so let's actually look at Polycam because that's probably the best example. So Polycam is like this website that it's like a website, but it also has a phone app, works on iPhone and Android, and it effectively allows you to do this type of like photogrammetry, right? This is a word that people use for this, but it's scanning these real world environments, right? And you can see that you can, for example, do the inside of a room or something like this, right? And it's pretty good. And sometimes when people ask me like, why are these techniques possible now and not possible before, right? Because in reality, this type of photogrammetry, this is decades old, right? People could do this decades ago, right? So like, why is this being done now and not before? Well, part of the reason is that the tools for this have gotten easier and easier and easier over time, right? At least when I was doing robotics research, the idea of like scanning the entire robot environment and creating a digital twin of it wasn't great because it was kind of too difficult to do, right? Like the tools just weren't quite there yet, and you would spend a bunch of time doing it. It wouldn't stitch together that nicely. So we're getting to the point where these tools like Polycam are just so good and so clean and so easy that you can effectively scan the robot environments, right? And in this paper, they scan all the different environments and objects that the robot is going to interact with, right? They also have to do some articulation, and this is still a manual process, right? So unfortunately, this is still being done by hand, and that is where you now create this scene. But now in order to kind of separate out the objects, right? Because as far as these scenes are concerned, there's no notion of like, what is an object? What is a flat surface, right? You don't have any of that. What is an articulated hinge, right? There's no sense of like this door opens and then these parts of the object can swing outwards. So all that kind of more physical relationships between the things in that scene still need to be done by hand. And you can see here they're basically tracing out the door of the oven and then adding that as a separate object. So they're creating this kind of entity component system, which is what you see in video games, right? The fact that you have objects and floors and physics, and these things can reflect light, these things can't reflect light, and so on. And that's still a very manual process. But the same way that the tools for scanning got better and better over time to the point that your average robotics paper could just scan the entire environment, I think the tools for taking scans and turning it into these kind of universal scene descriptions are going to get better and better over time, right? You can imagine in 2030 some kind of tool where you can just use like speech, and then there's a little agent that sits there and does all this like cutting out these points and then labeling it as door and then allowing the hinge and all that, right? So you can imagine a world where creating an articulated USD out of a phone scan takes 10 minutes, right? And actually one nice thing about this paper is they actually show you the exact time it took. So 3D reconstruction, GUI user study breakdown. So they tell you how long did it actually take to create the scene, right? So how long did it take to scan, make a second scan, to upload, and then kind of like create the little universal scene? It's about 40 minutes, right? And that, I think it's huge, right? People are sleeping on this, that it's so fast now that you can kind of scan the entire environment. And now you have a way better digital twin than what you see in a lot of robotics papers where it's like there's no, there's no environment. Your robot's standing in this completely bare bones world with just a flat plane that it's standing on. Reconstruction via block bundle adjustment. This is Dan. Photogrammetry is measurement of light and is broader. Yeah, there's like different nuanced words, right? That like Nerf versus Gaussian. There's like a million different ways that you can call this depending on the specific technique that you're using. But yeah, I guess reconstruction is a more specific term for this. How's it going, Ed? Okay. Once you actually have this scene, right, then you can go into steps 1, 2, and 3 here, right? So first step is to train a vision-based policy with supervised learning on D-Real, where D-Real is real-world demonstrations, right? So this is the imitation learning part, where you have a bunch of real-world demos, so some human driving this robot arm, right, with some kind of joystick to pick up the object, right? And that's this set of trajectories here, which are effectively an action, which is an end effector pose. EE pose means end effector pose. That's basically the position of the hand, right? So the position of the hand has some X, Y, Z position, and then it also has a orientation, which you can represent as a quaternion. And that is the kind of like the target, right? So whenever you say the action is an EE pose, what you're saying is that this is where I want the hand to be, right? So maybe your hand is right here, and then the action is like there, which means that what you're basically telling the robot to do is just move in that direction, right? And when you're using these end effector pose as the action, you need to have something that's called inverse kinematics, which is then figuring out what joint angles to use in order to move to that pose. And that's something that has been solved for a very long time, right? Where you can basically say, okay, here's this series of math basically operations that allow you to take that end effector pose and turn it into an actual joint angles. And there's a little bit of issues there, right? But because now you have this extra complexity, but in general, EE pose is easier because it's a little bit more robot agnostic, right? Whether your robot has 6 joints or 7 joints, you can still have some amount of transfer with this EE pose action versus if you had a joint space or action, then you would have less transfer between different types of robots that have slightly different joints. Okay. X is the object poses. So there's a little bit of oracle kind of data here. So sometimes when you're doing these robotics tasks, you tell the robot exactly where the object is, right? You see this OT point cloud here. So this means that you're cheating a little bit because you're basically telling the reinforcement learning policy, right, the actual neural net that is executing or deciding what the actions is. It knows the position. It knows the XYZ position of these objects, which is kind of cheating, right? If you have a system in your lab that allows you to basically, you have like a kind of like one of those tracking systems so you can tell where everything is, you can provide that to the robot even in the real world. But I don't know, ideally I'd love to see them remove that. Okay, but you're doing behavior cloning here. You're using supervised learning with these oracle human trajectories in order to push gradients into this vision-based policy that is consuming the point cloud and then the end effector pose, and it's outputting another target end effector pose. Mocap. There you go. That's the word I was looking for. Although I think here they're just using a point cloud, right? So this is probably just an Intel RealSense. Okay. 2, roll out the vision-based policy on the simulation rendered point clouds and collect a set of 15 privileged demonstrations with object poses DSIM. Okay, so now they take this behavior cloning policy, which is real, right, in the fact that it comes from these real-world demonstrations, and then they roll them out in the simulation, right? Rollout is just how reinforcement learning people call inference, right? They call it a rolling out, which basically just means doing inference with this little neural net in the simulated robot and then seeing what it does, right? So you basically have the vision-based policy from your behavior cloning, and you use that to create the actions. Then you basically just run that, and you're going to now collect a second data set, which is called DSIM, right? And because this is now in simulation, right, you now have the magical oracle like knowledge of like, hey, did this robot actually pick up the object? Did the XYZ position of this object in simulation go up, right? Did you actually see it touch it, right? Because in simulation, I can verify that for sure, right? I can verify that the robot actually picked it up and that it actually changed the Z position of that object, right? And there's ways to game this, right? So like one of the famous kind of examples is that in simulation, because of the way that physics is calculated with these kind of mesh-based simulations, you can push an object into a table, and if you push it into the table, eventually the force between the object and the table will be so big that the object will kind of pop out. So in these kind of like pick and places in simulation with RL, like one of the kind of cheat codes that the RL will learn is that it can push objects into each other to kind of get them to pop out, like you see in video games, right? Those kind of like glitches. But either way, you can still kind of do this filtering where you roll out this policy in simulation. You can start collecting examples of trajectories where it succeeded and examples of trajectories where it failed. And now you're going to take that, right? And this is called the replay buffer, right? Usually when you're collecting experience like that in a simulation with a reinforcement learning policy. And then you're going to fine tune it once more, right? So train a robust state-based policy with RL and a sparse reward, adding a BC loss fitting DSIM to bias exploration, and a prior on real-world transfer policies. Okay, so now you're going to do your RL. Simulated scene, object poses, EE-Pose goes into this state-based policy. You see how here this is a vision-based policy? So this vision-based policy is consuming the actual vision information, and that's what it uses to create the actions. But here you only have a state-based policy. And why do you need a state-based policy only, right? Doesn't that feel like a negative because now you've kind of lost some information? Well, the reason is because once you go to real, you don't have the kind of oracle knowledge that you had in simulation, right? In simulation, I know where every single object in the scene is. But when I go into the real world, I don't really have every single real object in the scene anymore, right? I have the proprioceptive information, which is just the robot joints, but that's kind of it. Maybe I have a mocap system that tells me where stuff is, but there's going to be error on that as well. So whenever you're going right from real to sim and then back to real, you need to kind of remove some of that privileged information that you had in simulation. Okay. I think let me see what else I want to show here. Human policies. We went over that. We went over that. We went over that. Yeah, I wanted to show this. So this is some of the results for their imitation learning versus their Real2Sim2Real technique, which they call Real2. And you can see that it's significantly better, like disgustingly better, right? So pose randomization, distractors, and disturbances. This is different types of kind of adversarial techniques. So pose randomization, that's okay. We're going to randomize the position of the robot and the object a little bit, right? Distractors means that, hey, when you're picking an object on a table, we're going to put some other random object on that table too, right? And distractors are very important because a lot of times in these robot pick and place papers, right, there's nothing else on the fucking table. It's like the robot is just picking one thing off the table. So it's like, like it's not hard to just pick the one thing on the table when there's only one thing on the table. So adding distractor objects and disturbances is like kind of what you see the Boston Dynamics people when they kick the robot. That's kind of what you mean by disturbances here. But look at the difference between pure imitation learning or behavior cloning and this Real2Sim2Real, right? You have 90% success versus 30%, 10%, 90%, 80% zero, right? So we're seeing that behavior cloning is just not good. And that's basically what I did. I feel like when I was working on this problem, this kind of like pick and place, right whenever deep learning came out, it was all like imitation learning and behavior cloning were very popular. You had RL, but like that didn't really work super well. So, we're starting to see techniques that do work very well. And I think a big part of that is because we now have the ability to kind of scan and capture the entire environment. And that's why when you scan and capture the entire environment, the sim-to-real gap, or the difference between the simulated world and the real world, is smaller, right? Versus before, when you didn't have this ability to create the entire scene, the sim-to-real gap would be just too big to traverse. With the distractors, Meta AI published a video today about adding people in their habitat sim. Yeah, so I mean, like, people as distractors is a real problem. I remember when I was doing this, one thing that would happen is that you had this robot in the lab, right? It's operating based on vision, but all the data that was collected never had humans standing around it, right? So you would basically, whenever you were demoing this to a bunch of customers, you would have like 10 people standing around the robot. And if you have 10 people standing around the robot, now the vision information that you're getting is very different from the vision information that you saw in training, because in training, there was nobody else in the lab. So the robot's kind of used to operating kind of with just one person in the lab. But when you have 10 people in the lab and there's like all this movement in the cameras, right? That's a completely different part of vision space. So then the robot behaves differently, right? So you have to kind of add these distractors in simulation or in order to make it robust to distractors when you're actually running it in the real world. Okay. Let me take a sip of yerba mate and then I'll go into this paper. All right. The next paper I want to talk about is this one. This is VR Robo, a Real2Sim2Real. So there's that terminology again, framework for visual robot navigation and locomotion, on the 3rd of February 2025, coming out of a bunch of different Chinese institutions here. So this is a very, very similar approach, right? Where basically Okay, let me actually just go into this. RGB only policy training and deployment. So RGB only means that you have no depth sensors, no LiDAR sensors, and no SLAM, right? SLAM is the simultaneous localization and mapping, where you're using something perhaps like visual odometry to kind of like create this 3D environment. But the robot's not doing that, right? It's just consuming some picture, and then the policy is outputting some action, right? Where the picture's just a 3-channel RGB. But the let me see what else. RGB-based perception, like egocentric navigation, 3D Gaussian splatting, based scene reconstruction from multi-view images, and then mesh-based physical interactions. And this is the important part about this paper, is the fact that they're using 2 different types of simulation here, right? So Sim2Real, which is kind of the more classic approach now, one of the reasons it fails is because standard simulators struggle to replicate the visual fidelity and complex geometry of real-world environments, right? Gaussian splatting has emerged as a promising solution for creating real-to-sim digital twins from real-world data, right? These kind of like, this is not Gaussian splatting, but it's kind of similar, right? Where you're kind of using a bunch of pictures from a cell phone to create this kind of digital twin. All right. Real2Sim2Real is a hybrid where you start with a Gaussian splat mesh hybrid representation. And what does that mean? Okay, so let's go here. So the problem with these Gaussian splats, as we said before, is that there's no notion of like objects or flat planes, right? There's nothing that's saying this is the floor and this is going to be hard and flat and you can stand on it, and this is the person's arm and that's going to be squishy and soft, and when you push it, it's going to move, right? There's no like physics in that, right? But luckily, we have a bunch of physics, right? People have been working on video game physics for a very, very long time. So the classic kind of video game representation of meshes with textures on them, in this case, you don't need the textures, but the meshes, all the physics, we have tons of different physics that works between 2 meshes, right? You can get the friction between 2 meshes. You can get meshes pushing off of each other. People have deformable meshes, right? Like all the game engines have physics that aren't perfect, right? They're not quite a perfect simulation of the real world, but the physics tech stack for meshes is significantly more advanced than the physics tech stack for Gaussians. And even Gaussian splats, there is work that is starting to recreate some of this physics tech stack within Gaussians, right? Where you can start having kind of a rigidity where objects are rigid. You can look at the friction. You can look at the deformability. Could I explain the title of the stream? This is a question from Ario. Real2Sim2Real. It's basically just what these guys are writing here, except I wrote it with the numbers 2 instead of 2. So Sim2Real, like this, the way that the cool kids write it is sim, then the number 2, because TO and then TWO, which is how you say 2 in English, is very similar. So you can write it Sim2Real, or you can write it like this, right? So it's the same kind of concept where Real2Sim2Real, you could write it like this, which I think looks kind of ugly, or you could write it like this, which looks kind of cool. That's the whole point. Okay. But let's go back to this paper. We build interactive simulation environment with Gaussian splat mesh hybrid. Okay, yeah. So they're doing the same thing that they did here, right? Where they're reconstructing this digital twin, but they're basically have 2 slightly different versions of the digital twin. They have the Gaussian one, which is very good at visual fidelity, right? It looks very real. And then you have a underlying mesh scene that is going to allow you to take your simulated robot and go up this ramp, right? So unfortunately, this mesh scene, somebody had to make that by hand, right? So if you look at this paper, the entire paper is in the same environment. It's only one environment, right? Compared to something like this where they have multiple different environments where they're showing you their work. And this one, there's only one environment because some human had to create this exact mesh representation that aligns perfectly with a real-world representation, right? And there is work that is starting to do this in a more automatic way, right? If you put on a VR headset, whether that's the Apple Vision Pro or the Quest 3, right? They're already doing versions of this, right? Where they're starting to create these kind of more mesh. They scan your environment, they create kind of a virtual version of your environment, and then they start to recognize the flat surfaces and put planes on that, recognize where the floor is, put a plane on that, recognize where your couch is, and kind of create a mesh that you could eventually interact with digital systems, right? This is how you're going to get a mixed reality type world where a mixed reality character in your headset will be able to sit down on your couch. It's because your couch has some specific boundary that mesh representation that's being created for it. Okay. We first reconstruct the digital twin. So here's the digital twin. Now you have a photorealistic and interactive simulation, right? Versus here, you just had the photorealistic simulation. Here you have the photorealistic and interactive simulation, right? Where you can actually go up this ramp. Visual observation, domain randomization. Domain randomization is when you change variables, you randomize things within the domain, right? So within the domain of, for example, the Gaussian splats, one thing you can do is you can mess with the lighting, right? So Gaussian splats, a lot of time they have this component called the spherical harmonics, which is something that determines what it looks like from different viewpoints, right? So you can expect that a shiny object, when you look at it from different viewpoints, certain parts are going to suddenly reflect light, and then they'll have a different appearance from a different viewpoint. But you can do this domain randomization also in mesh-based representations. Domain randomization in mesh-based representations might consist of changing the friction coefficient, right? So you can say, okay, this ramp, where whoever built this scene, this mesh-based representation scene for this ramp, they decided on some friction coefficient for that ramp. So a type of domain randomization that we could do for that would be like, okay, anytime you start up the simulator, we're going to pick a value within some random human-defined bucket of like, okay, the friction coefficient can be like 0.001 or it can be like 0.9, right? And that'll give us a wide variety of simulated environments so that the policy that we train in this simulated environment can hopefully generalize to a variety of different friction coefficients. Okay. What else do we got here? And then sim-to-real policy deployment. Okay, so you have your policy. It's producing actions. It's going into the simulator. The simulator is creating observations and then robot states. Those are then being fed into the policy in addition to the observation, which is just an RGB image. And the policy produces another action, and then you just kind of keep repeating and repeating and repeating, right? Here it says 3DGS, and there's like an arrow here going from the 3DGS to the simulator. So why do you need that? Well, the whole thing with Gaussian splats is that it's a way of creating a photorealistic image of a thing, but you need the pose. You see this pose, you need to know where you are at. So for example, in something like this, how does it know the rendering of this is dependent on the view, right? So if I go like this, oh, this is terrible. The loader takes forever, but if I change the view of this, right, the appearance is going to change. So in order for this Gaussian splat to render, I need to give it what the pose is. And luckily, because I'm in simulation, I know exactly what the pose is, right? I can tell you the exact position and orientation of the camera inside this robot, and that will allow me to create a photorealistic Gaussian splat from that exact viewpoint. I add a little bit of domain randomization, and then I feed that as an RGB image into the policy. Okay, and then here, zero-shot policy transfer to real world. Zero-shot basically means that they didn't have to do any additional fine-tuning on the real world, right? This is all trained in sim, and then they just transfer it onto the real world, right? So how is this real to sim to real? Well, kind of similar to this, right? In this one, it's a little bit more real to sim to real because you're starting from these behavior cloning on real human demonstrations. In this case, they're using the real to sim to real, but they're mostly kind of referring to the fact that this Gaussian splat is created from the real. So they're creating the simulation from the real, and then they're training in sim, and then they're deploying to the real. So that's how it's real to sim to real in this case. It's a little bit different than the real to sim to real that they do in this paper. But it's the same kind of idea, right? The underlying core idea in both of these papers is this idea of like, hey, we've actually gotten a lot better at creating simulations that are similar to the real world. So we can now do stuff in simulation that we couldn't do before, right? Okay. Which leads us to the paper that I actually wanted to discuss today, is this one here. Let me take another sip. Really enjoy your paper walkthroughs. I appreciate the love, Brandon. Dan, have you ever heard of a paper that uses sparse voxel octrees or OpenVDB level set or something as the geometry? I feel like the meshes seem like the wrong thing to use, but I'm no expert. Yeah, so what a octree is, what Dan is talking about there, an octree is kind of like a way of organizing data into this like data structure that is kind of like a graph where it kind of, actually, let me just type it rather than trying to describe it. It's like this, right? So when you're storing information, right, you want to store it in a way that's fast to get that information, right? So for example, if you're familiar with Python, you have something like a dictionary, right, where I can give you the key, and then with that key, you can go and retrieve the specific information relevant to that key, right? There's the key and the value, right? And that's really underneath that, there's a very popular data representation that stores all of that in the computer memory such that it's fast to retrieve, right? That's the whole point. An octree is basically the same thing, but for 3D space, right? Where I'm storing this 3D information, but I'm storing it in this kind of way where you see that the resolution is kind of like built in, where it's like, okay, first you got to tell me which part inside this voxel. A voxel is just a fancy word for like a cube in 3D space, right? We have 3 dimensions of space, so if you kind of have some bounded area of 3D space, it's going to look like a cube. So an octree stores information inside this kind of cube within cubes within cubes in such a way that it's fast to retrieve and fast to deal with, and it's relatively efficient to store that, right? But why are they using meshes rather than octrees? I feel like the problem is that octrees are kind of an exotic way to store 3D information, right? They're different from a Gaussian splat. A Gaussian splat isn't storing it inside an octree. What a Gaussian splat is doing is it's like a set of points, and then each of those points, there isn't like a necessarily there is a position for each of those points, but they're just kind of this giant set of points, right? And even within a Gaussian splat, you're still doing things that are similar to like an octree, right? You're like rendering specific tiles, and you're like aware of where the splats are within the tiles. But why are they not using an octree? Well, because the Gaussian is very good for visual fidelity. That's what you want out of the Gaussian. And then the mesh is really good for physics interactions, right? Because that's what video game physics are based on, right? Like a lot of smart people tried to make objects bouncy and deformable and make the friction good in video games for decades and decades, and that's why mesh-based representations have the best simulated physics, not because they're necessarily the best 3D representation for physics. In fact, I think that Gaussian splats will eventually have physics that are better than the type of mesh-based physics that we have now, but the mesh-based physics that we have now are the result of decades and decades of engineering work. So that's why they're using meshes, because the physics of meshes, right, the collisions, friction, the deformability, all those things there's a lot of people that have put a lot of engineering effort to make the collisions with meshes extremely fast and pretty good, versus like something like an octree. Like, okay, tell me how 2 objects that are defined in this kind of octree style, if you shoot them at each other and they bounce, like, how does that work, right? Who's done the physics for that? Okay. Meshes give you ray casting, which is really common for collision detection algorithms. Yeah, and they also give you a way to determine kind of the force between objects, right? You can like look at how much the meshes kind of penetrate, and then that allows you to determine how much force there should be whenever you actually push off, right? And same thing with friction, right? You can determine, okay, well, what's the actual surface area of this object on this object, and that can help you determine the friction between those. Okay. But let's get to this, though, because this is the paper that I really wanted to talk about here. How's it going, Pratik? ASAP. Like I said, it's a Jim Fan paper. It's NVIDIA. It's Carnegie Mellon. The demo is absolutely great, so I couldn't not talk about it. And let me just start with the demo, because I think this is the coolest part, right? So you have the Cristiano Ronaldo, like after he scores a goal, he does this thing where he like jumps super high and he like lands on both his knees. You have the Kobe Bryant jump shot. Like, look at this. This is some of the like most agile kind of humanoid stuff I've ever seen. You know, we really are making a lot of progress very quickly. So first of all, let's start with the robot. What is this robot? So this is the Unitree G1, this one right here. All right, so you can actually see it's actually really small, right? It's very tiny. It's a little tiny little robot, right? You can see this is the human, right? Out of all the robots, is the smallest, but that's also a feature, right? Because at the end of the day, it's like the people at Unitree know that this isn't going to be the robot that actually like does things, right? This is more of a research platform, right? So really what Unitree is hoping for with this robot is not that it's going to pick up 700 million boxes in a warehouse, right? That's not what this robot's going to be used for. This robot's going to be used for research, like this paper, and then the second version or the third version or the fourth version of this robot, right? The GR2, the GR3, the GR4, those will be the ones where, okay, now we actually need to maybe make it a little bit bigger so that it can actually pick up boxes versus just being a little tiny humanoid. But if it's just a research platform, right, you might as well make it small, right? It makes it small, makes it a little bit cheaper. The motors can be a little bit cheaper. It uses less power. It's easier to ship. So I actually really agree with making it kind of small. And one thing I didn't like about this picture is that it gives you kind of the wrong impression here. So they have a bunch of different robots here, and they have all the American robots, right? They have the Digit from Agility. They have the Atlas from Boston Dynamics. This is the electric one, not the old hydraulic one. You have the Optimus. You have Apollo from Aptronic. You have Figure. You also have the Neo. This one's all, like they put the Norway flag here because the original team is from Norway. But I feel like at this point, 1X is basically American. I think all their AI stuff is done in SF, so this is basically American. But you know, there's a lot more Chinese humanoids, right? There's at least like 4 or 5 different Chinese humanoids that they didn't put in here. So this picture makes it seem like the humanoid robotics is kind of dominated by American robots, but in reality, there's way more Chinese humanoids than there are American humanoids. And I think the very best humanoids, which I think is this one right here, right? The little G1, at least for right now, just because these are still kind of just research platforms. I feel like this is the best one, the G1 Unitree. Okay. But that's the paper. Let's actually learn what's going on. So, right, we saw the demo, amazing team. So let's actually dig in and see what exactly is happening here. So we're not going to start with this one because this is actually a little bit confusing. I think I wanted to start with this, right? So how is this Real2Sim2Real, right? The name of the stream is Real2Sim2Real. So how is this paper Real2Sim2Real? Well, you're starting from real, where you have human motion from video. Then you're using tram to turn this into SMPL. So SMPL is this little kind of, it's like a standard, right? It's basically a definition of like, okay, here is a digital version of this human. It's used for pose tracking and pose detection, right? Pose tracking and pose detection is the problem of taking some kind of RGB video or maybe a sequence of RGB videos or maybe multi-view videos or some kind of real-world information, real-world visual information, and turning it into a digital human that is moving in the same way, right? So the whole point with this simple is to create one standard format that everybody can kind of use so that if you record yourself jumping in this mocap studio, then somebody else can use that for their project, right? It's kind of like a standard. So SMPL motion from this real human video, right? So at this point, the way that you're going to do that is with some kind of deep learning based model, right? So the way that you're going from this RGB monocular image into this SMPL motion, which is just here's a value for each of the individual joints and then that over time, right? Some kind of deep learning model tram is used for that. Okay, now you're going to take that motion, that SMPL motion, and then use it as effectively the target in RL. So actually the Real2Sim, this first step right here, is basically exactly the same thing here, right? Where you're first using what is effectively kind of like behavior cloning, right? So here what you're doing is kind of behavior cloning or imitation learning, where you're using reinforcement learning to try to track. You see these red balls? You're basically saying, okay, the reward for the reinforcement learning that is operating at this step is to basically make the ankle on that red ball. If the ankle is far away from that red ball, no reward. If the ankle is right on that red ball, high reward, right? So you're effectively doing this kind of like imitation learning of the original human trajectory. All right, that's the first sim or Real2Sim. Okay, and then you're going to go from sim back to real. So now you have this RL that's been trained on this simple motion. You have the fancy kind of stuff that they're doing in this paper, which they call here motion from retargeting. It gets a little nuanced, but they're basically going sim, a little bit fancier sim with slightly different stuff. There's like this delta action model that we'll get into, and then they deploy it on the real robot, right? So there's your real to sim to real. You're going from the real human motion into sim, where you can use RL, and then you're taking all that learning that you did in RL in the simulation world and then deploying it zero shot into the real world, and now you have it, right? You have a way to go from real to real by going through sim. Okay. Mesh is good for retaining the topology versus splats aren't topology aware. Yeah, I think so. There is work to do that, right? I mean, I do want to make this clear that I feel like long term, Gaussian splats are a better 3D representation than meshes, right? The reason that meshes are just more useful now is because we've literally spent decades and decades of engineering meshes, right? Like every single game that you've ever played is like mesh based, you know? So like think about just like the raw amount of hours of engineering that went into developing the physics models and trying different physics models in mesh based representations. I think that as soon as you have like a decade or two of work into Gaussian based representations, right, which are still super new, the physics interactions that you're going to be able to get with Gaussians are going to be so much better than the physics interactions that you're going to be able to get with meshes, right? But we just need to wait a little bit for Gaussians to become more mainstream and people to come up with cool ways of doing friction and deformability for Gaussian-based representations. I think Ario is basically talking about something like that. Topology-aware 3D Gaussian splatting, leveraging persistent homology for optimized structural integrity. What a name. What a name for that paper. Okay. Let's go back to this. So real to sim to real. And then I wanted to go into this. Yeah, okay. So this is a very good paper. And part of the reason it's a very good paper is, one, because the demo is really fucking good, right? But two, is also because they have very good ablations here and baselines, right? So whenever you demonstrate some new technique, right, you kind of want to show me how it would have worked with older techniques, right? I want to be able to see the difference between your new technique and the old technique so that I can say, okay, well, this new technique is definitely way better. So they're going to be comparing two variants of their techniques here, which is delta dynamics and delta action, with kind of a more classic way, right? You have your vanilla and you have your sysID. So vanilla is, they call this model-free RL training. This is basically just like RL in the simulator, right? So effectively this one right here, right? This PPO from scratch, right? This orange one that basically just fails. That's going to be the baseline, right? The most basic way of doing it. You have your neural net policy. It's consuming states from the simulator. It's producing actions, and those actions result in some kind of state. You can then get the reward from that state. Maybe you're looking at the distance between the goal target and the ankle, right? So something like this, that'll give you some reward. That's the reward function. Then you just literally use that to push a gradient back into the policy, and that's effectively just RL from scratch in the simulator. This thing doesn't really work, right? Like, one, it's very hard, and then even if you train a good policy like this and this RL from scratch, whenever you try to deploy it on the real robot, right, this kind of like vanilla real to or sim to real, it's not going to work very well, right? Because the simulator is just not the same thing as the robot, so you're going to have all kinds of issues. Okay, the next baseline is going to be what's called sysID or system ID. And sysID is actually very popular. People use this all the time, even today, right? And what you're doing there is that you have these parameters in your simulator, right? So there's little things in your simulator. So for example, in the previous paper, right, the friction coefficient of this ramp, right? So you're kind of picking that, but another thing that you can think about doing is kind of picking it based on the real ramp. So like, is there some way for me to determine what the optimal value of what value should I use for this friction coefficient so that it's the closest as possible to the real world, right? And that's what sysID is doing, is trying to identify the parts of the simulator or the little parameters that I'm going to set such that this simulator is more similar to the real world. Because the closer I can get the simulator to the real world, the better the better this policy is going to be, right? So whenever I deploy this policy, which I train entirely in sim, into the real world, if this simulator is very similar to the real world, then that sim to real gap is going to be smaller, and I'm going to be able to transfer that in a better way, right? My policy is going to perform better. So we actually have the exact parameters here. So for sysid, again, the parameters in the simulated model, you're trying to align them with the real world. And you're searching for the best parameters along certain discrete ranges by replaying the recorded trajectories in real with different simulation parameters, and then fine-tuning the pre-trained policy in Isaac Gym with the best sysid parameters. So specifically, the sysid parameters here are going to be the center of mass shift, CXCYCZ, which is basically, there's going to be some center of mass for this robot, right? Paperpile, which is the program that I use to read these papers, there's so many pictures in this paper that it takes forever. But in simulation, you're going to have to define where the center of mass is for this humanoid. And usually it's even more complicated than that, right? You're defining kind of for each of these joints, you might have you have to define the center of mass, but then also things like the inertia, right? The moment of inertia, different shapes, different 3D shapes, and the distribution of mass within those 3D shapes is going to determine the inertia of this, for example, femur area, right? And that's actually incredibly difficult to do, because think about the way that mass is distributed along this thing, right? There's going to be more mass maybe in specific parts where there's metal, and then there's going to be less mass where there's kind of empty holes, and you're never going to be able to recreate that in simulation. So already, whenever you're trying to define a center of mass and kind of the way that the inertia is going to work for each of these different joints, your simulation is going to be way off, right? So sysid is about trying to find the closest possible values for those. So the center of mass, the base link mass offset ratio, and low-level PD gain ratios, KP and KD. So PID controllers, this is what's actually executing the command on the robot, right? So for example, if we go back to the first paper, right, this robot here, it's producing these actions, right? Or maybe let's go to this one. This one's a little bit. You see the action is this EE pose, right? So when you actually give the robot this end effector pose, there's additional steps beyond that, right? So then there's your inverse kinematics. That's okay, determining based on this EE pose and based on my current pose, what is the position of the joints for each of this for the position for each of the joints on this robot. Okay, and now that I have the position for each of the joints on this robot, there's something even lower level than that, which is a little PID controller that is basically taking the current position of the joint and the desired position of the joint. It's maybe also taking into account the velocity of the joint, maybe some window of previous positions, and then it's using that to determine the actual final command. Because at the very end, right, the real final thing that is controlling the robot is electricity that is increasing or decreasing, right? You have this little magnet in the joint, and then basically you have to determine how much electricity you're pushing in, and that is effectively what's coming out at the very end, right? So these PID controllers, they're kind of determining that, and you have one of these running for each of the joints. So you see how from I all the way from 1 to 23, that basically refers to the fact that there's 23 joints on this robot. Let's wait for the thing to load so you can see the 23 joints. See that? You got shoulder, roll, yaw, pitch, elbow, hand. There's no hand here. And I think that's eventually we're going to move to that. So maybe one kind of negative thing about this paper, and it's not even that negative just because what they did is already pretty impressive, but you see how the hands are just not there, right? There's no hands. Basically, it's all just body, but you can imagine that at some point we're going to have to do this with the additional hand, but the hands you're basically going to double this number, right? People are saying that the Tesla hand has 21 different degrees of freedom. So imagine adding another 21 joints for each hand. So you're basically tripling that. You're going from 23 joints to 23 plus 21 for the hand plus 21 for the hand. So your state space is going to grow significantly if you have hands added. So right now we still haven't added the hands. Okay. Maybe let's talk about this metric just for a second here. So how do we report here? For example, they're comparing the 4 different techniques here: vanilla, sysid, and then the delta dynamics versus the ASAP, which we're going to get into. But what is this MPJPE, right? What the hell is that? This is tracking error of the global body position, and the root relative mean per joint error. Okay, so the metric that they're fundamentally using is the basically per joint error, and then the effectively average of that, right? So they're saying, okay, this is the position of the joint. So you see these yellow little dots here, that's the target, right? They want each of the little joints to be at that yellow target. So you can see here with the vanilla, which is open loop action only, which means that it's basically just executing the action that comes out of the policy that was trained in this case, Isaac Sim. And one thing that they do here in this paper that's kind of interesting is that they do sim to sim in addition to sim to real, right? So we've seen in this paper, this one here, maybe not this one. Which one am I looking for? All right, I'm not going to find it, but you're taking your sim policies and you're deploying them on the real policy, right? That's called sim to real. But what you can also do is you can take your sim policy and then deploy it on another simulation, right? A slightly different simulation, because that slightly different simulation is going to have slightly different quirks, right? The way it does the friction might be different, the way it does the momentum and all of that might be different. So those little differences are going to result in a sim to sim gap, right? That's kind of similar to the sim to real gap, right? So sim to sim makes it easy to kind of compare, because whenever you do sim to real, it's hard to come up with this error exactly, right? Because you don't actually necessarily know, unless you have some kind of mocap tracking system, how good or how bad the sim to real transfer was, because it's hard to measure the quantify exactly what's going on in the real world. But sim to sim is a lot easier to quantify because it's also a simulator, so you can know exactly where everything is. You know where the target was at every single point, so you can get this exact error, right? And you can see here in the vanilla, at some point it starts getting out of phase. You can let's zoom in a little bit here so you can see this. But you can see here it starts off good. It's trying to walk, and then you see the target is kind of going, it's walking, but then the in simulation the robot just falls, right? So the ability of this policy trained in simulation to transfer to another simulation is basically garbage, right? With sysid, right, where now this is weird because it's sysid where you're trying to basically identify the sim parameter. So you're trying to do sysid to get one simulation to match the other simulation. Okay. But if you do that, which reduces the difference or the gap between those two simulations, now you can see that it actually works a little bit better, right? It still eventually fails and it doesn't reach the target there, but you can see it lasts a little bit longer, right? So sysid reduces the sim to sim gap the same way that sysid will reduce the sim to real gap. Okay. Now let's get into the kind of two fancier things they do in this paper. They call delta dynamics and ASAP, which is their specific version of it. Okay. Let's go up here. All right. So we're going to start with this one. Let's start with this here. The delta action model is defined as delta AT, and this is a little delta. This is a little model right here. So you see this little model parameterized by theta, and it takes in states and actions at some time t, and then produces this delta AT. So it produces a delta action. Right? So what is this action? This is a corrective action. The corrective action, delta A, is added to the real-world recorded actions to account for discrepancies between simulation and real-world dynamics. Okay. So what this... It's kind of like a type of... It's similar to sysid, right? At a high level, it's doing something very similar, where it's basically trying to close the gap by making the simulator closer to the real world, right? But in sysid, what you're changing is these little numbers inside the simulator, right? You're actually changing simulation parameters. Versus in this delta action model, what you're doing is you're training a little separate model called the delta action model that just changes the action a little bit, right? So you're going to train a policy. That policy is going to produce some action, and this delta action model is just going to say, okay, well, here's a little nudge which will make the action slightly different so that it kind of looks more like the action that the simulator would expect, right? So here's an example. Consider a scenario where the simulated robot can jump because its motor strength is overestimated. So in the simulation, your motors or your simulated motors can do like this crazy, the power of those simulated motors is a little bit more than the power of the real motors. So the policy that learns how to jump in the simulation it's going to be able to make use of those very strong motors. But when you then take that policy and try to deploy it in the real world, the motors don't have that same strength, so the real robot is not going to be able to jump due to the weaker motors. So the delta action model will learn to reduce the intensity of the lower body actions, simulating the motor limitations of the real world robot. Right? So it's kind of like a little model in between that adjusts your actions so that you get a kind of a similar effect as SysID. Okay. And then you have the modifying the simulator dynamics. The state at time t+1 is going to be equal to your simulation function, which takes in some states, takes in some action, and then in this case, you're going to add that little delta action from the delta action model, and then that's what you're actually running in the simulator. AR is the reference action recorded from real-world rollouts. Okay. During each RL step, the robot is initialized at the real-world state. Reward signal is computed to minimize the discrepancy between the simulated state and the recorded real-world state. Action magnitude regularization term. What is an action magnitude regularization term? It's a additional term that you add into your objective function that says, okay, if your action, the magnitude of your action here, right, if that is very large, if you're taking very big actions, right, if you're doing very jerky motions where all of a sudden your hand is not moving and then you're like moving very quickly, we're going to penalize that, right? This value is going to get very big, and now your loss is not going to be small, right? In this case, if it's the reward, you want to maximize it. If it's a loss, you want to minimize it. But either way, you can just add a negative in there, and then it works for both. But effectively, you just want to not have these big actions. And then you can see here they're also using PPO. Okay. Let me see. Nice. Need a more scalable approach for such an increase in number of joints in the future? Maybe some kind of ensemble of models, controllers cooperating? Yeah, I mean, there's different ideas about what's going to happen there. So I'm answering this question by Brandon here. Some people think that the way that this is going to work is that you're going to have a separate model for the hands and you're going to have a separate model for the torso, right? And this is kind of similar to even just a couple years ago, and even nowadays, people will have a separate model for the upper body, right? And they kind of separate it out, for example, manipulation and locomotion. You'll have one team that works entirely on locomotion, is really only interested in kind of the legs, and you might even see like just torsos where the only thing that you have is legs, right? And then you'll have a different team in the same company that works on manipulation, where, okay, the only thing they care about is these arms. But you're seeing more and more that we're combining these together, right? Rather than having one model that does the manipulation and torso part and then one model that does the walking part, you're starting to see, and this paper is a very good example of one model that does both of them, right? And I think the same thing is going to happen with hands, where people right now are going to have, okay, we're going to have a separate model for the hand and then we're going to have a separate model for the body. But I think you're going to see the same exact trend where eventually those two things are going to merge together and you're going to have one thing that's controlling all of it, right? You're going to have one policy that has the state space and the action space that includes all the body joints and all the hand joints, right? So the policy, if your robot is standing there in front of a table and it's manipulating objects, that policy is still producing actions for the ankles, right? And I think that's important because even if you're sitting there cooking, for example, there's a lot of motion in the ankles and the knees and stuff. You're very subtly moving your lower body in such a way to like change the center of mass so that you can, whenever you pick up an object, you're very slightly leaning backwards, right? So that the object doesn't cause you to fall forward. So I think that we're probably going to see all of these things combined into one policy rather than what we're seeing now, which is this kind of like piecemeal, like modular kind of approach, right? Like the general story of robotics and especially deep learning based robotics is that what is used to be a modular kind of approach where you treat these problems separately, which is what good engineers do, right? Good engineers break problems into different pieces and then they solve each of the problems separately. But what we've seen over time is that eventually a more simple approach where you just kind of control the entire robot rather than kind of like piecemealing it out like that works better. So I think that's going to happen with the hands as well. Okay. We were talking about the delta action model, let's go to this. So this is the main figure in the paper, but I kind of wanted to touch on some of the other stuff before we went to this one, because I think this one can be a little bit confusing initially. So now let's look at the main one here. Okay. So motion tracking, pre-training, and real trajectory collection, right? This is a real to sim to real. So the first reel, you're starting from these human videos data set, right? So you have a RGB video of Kobe Bryant doing this jump shot. And then first thing you do is you get the pose, right? Into that simple pose. And then that becomes effectively the target that you use for just standard behavior cloning or imitation learning, right? Where you're kind of just trying to imitate that in RL. And this is your real to sim, right? You're taking this real trajectory and then you're trying to train something in sim, which kind of does that real trajectory. Then, now that you're in sim and you've kind of, you have this policy that kind of does what the human does, then you're going to use RL to effectively train it to actually work, right? Because the problem is if you just take this reel and you put it in the sim, the robot's just going to fall over in sim every time. But in sim, you can use RL to effectively learn how to not fall off or fall down, right? And then once you do enough of this RL here, right, where this little fire refers to that you're pushing gradients from some reward function that's coming from your simulator. Your simulator's taking in actions and it's giving back states and observation into this policy. Then you can take that and then train it, right? Do this delta action, do some sysid, right? Some way to reduce the sim to real gap, and then go back to real, deploy it on the real robot, and now you have something working, a policy that works on the real robot and does what Kobe Bryant did, right? So there's this sim, or real to sim, back to real. Okay, so that's this first part here. Let's go into these other parts here. Delta action model training. Okay, so this is a little confusing because it looks like the delta action model is like consuming all of these states, but it's really one inference step is just this first part. So the very first thing you start with is this reference state and reference action. So reference state, reference action. This is what I did. I think it's the, let's go to the exact definition. Here we go. Motion capture device and onboard sensors. So these guys did have mocap, right? So they do kind of know, even in the real world, they do know where the robot joints are. So the negative with that is that if you went and you took this robot outside where you didn't have mocap, you won't be able to have that. But inside the lab, you at least have the actual position of the joints. But you might not have that when you go into the real world outside, right? The only thing you might have would be the onboard IMU, right? You might have the like trunk center rotation, center of mass, angular momentum, things like that. So the state is PT base, VT base, alpha T base, omega T base, QT, and QT star, or QT dot, right? And these are the robot base 3D position, R3, so 3 numbers. The base linear velocity, right? So the velocity of the center of mass, the velocity of the robot. Alpha base is the robot base orientation, represented as a quaternion. That's why it's 4 numbers, right? Omega T base is the base angular velocity, right? So almost like the rotation speed. And then you have this 23 dimensions for the vector of joint positions, and then 23 dimensions for the joint velocities. These are the actual, you can get pretty much all of these, right? You can get the orientation and the angular velocity and the linear velocity from the IMU. The 3D position you can't really get from the onboard IMU. You're kind of like dead reckoning it a little bit. The joint positions you can definitely get from the robot at all times in any location. And then the joint velocities you can also kind of get from the real robot at any time. Okay, so let's go back up here. You're taking in your state at time 0, your action at time 0. That state at time 0 is going into this delta action model, which changes it a little bit. You can see how this action at time 0 is changed into this action at time 0 prime, right? Because the delta action model is basically just adjusting that a little bit. It's saying, okay, this is the action that you would take in the real world, but now we're going to take a simulated action, which is going to be slightly different, right? We're going to adjust that with a delta. The simulator is going to take that action in the current state, and then it's going to produce the next state. So, okay, it's if you're in this state and you take this action, you're going to get to this state, S1. Okay, then we take that S1 and then feed it back, and we just repeat this process, right? And you can look at the S1 and then look at the S1R and then say, okay, how different is the state that I ended up in the simulator to the state that I wanted to get in the real world, right? So like how different is my knee position in the simulator to the knee position of Kobe Bryant here, right? And that's how you're training this delta action model, right? So initially, you're really just training this delta action model to kind of mimic or adjust the action as much as it can such that the simulator matches the real world. So first you're training this delta action model. Then once you have that delta action model, you freeze it. So now you freeze it, right? You're not pushing gradients into that anymore. Now you're just pushing gradients into the policy, right? So before you were using effectively this reference motion to train this delta action model, which is kind of closing that sim-to-real gap. And then you're using that delta action model, which allows you to kind of make this simulator more like the real world, and you're using it to train the policy. So now you're actually pushing gradients into the policy such that it does whatever this reinforcement learning objective is here, which is probably like matching joint angles or something like that. All right. And then once you do that, then you can take that policy and deploy it on the real world, take out this delta action model. Here we go. Align simulation physics. That's already what we did. See, now they removed this delta action model. So now this delta action model, you don't actually need it on the real robot anymore. You get rid of it, and your policy just takes directly the state coming in from the robot, and then it produces some action, and you just execute that action on the real world physics, right? So this entire delta action approach is really just basically training this little model that tries to close that sim-to-real gap. We might be back. Okay, I think we're back. Hello. Okay. I'm sorry about that, guys. I don't know what happened. I literally didn't change anything. I have like a pretty complicated setup right here because I have like my own like multicasting basically. I stream from this Windows computer and it sends it to this Linux box that I have that then shotguns it to X, YouTube, and Twitch. So all three of those. And sometimes OBS does not like that. I don't know. There's a lot of different pieces here. What kind of neural nets are these delta models generally? A sort of alignment? Okay, so we can figure it out. I'm pretty sure in this paper, these are just like little MLPs. Here, if we control Elf MLP, we'll probably find it. Jesus. No matches for MLP. Delta model. Model. Residual action model. Maybe it's at the end of the paper. I'm trying to find the exact thing. But you can just tell based on this picture, right? So like, for example, in this picture, this is a little multi-layer perceptron, right? This is also a little multi-layer perceptron. Let's go to the appendix. Usually they kind of tell you in the appendix what it is. Or even better than that, we could go to the actual code because I think they open source the code with this. Neural dynamics model, residual dynamics model, dynamics model. Come on, guys. Where's the model? Tell me what the model is. For real world, baselines, Isaac Sim, SysID. Okay. These are, I'm trying to find it. I'm not going to find it. But based on these pictures, these look like little multi-layer perceptrons, right? So this is actually very different from here, right? Because in this paper, when you're using these vision language action models, right, these models have all that internet data inside of that, right? The language model that's inside that VLM has all the internet knowledge inside of it, right? And the image encoder, which basically just takes your raw RGB and turns it into that sequence of image tokens, that has a ton of knowledge as well, right? Because these image encoders are usually trained with some kind of like masked self-supervised loss, and it's like literally millions and millions and millions of images. So these vision language action models actually have a ton of intelligence in them already, right? So it's like, it's not like you're trying to almost build this intelligence from scratch. You're just kind of like eliciting the right set of neural programs from what's already in there. That's different than what you're seeing in papers like this, where they have just a little multi-layer perceptron, right? The policy is just a couple little layers of a neural net, right? Like kind of like the same type of neural net you would have seen like 10 years ago. But when you take this approach and you replace this policy with something like this, that's where you see the magic. I feel like this is kind of the point where I was getting at, where I was saying that there's a difference between kind of deep learning before language models and deep learning after language models, right? Where a lot of people in robotics are still kind of stuck in this like kind of like 2018 mode of thinking, where they're like, hey, classic robotics, which is kind of like you actually have a physics based model of your robot and you're kind of just doing standard control stuff there, versus deep learning based robotics, where you're using this little tiny MLP. But there's actually a huge difference between deep learning with an MLP and deep learning with a VLA or a VLM, right? Or like you're actually using an LLM there, right? Because we read a paper last year at this point that I think it was called LLMs are optimal pattern recognition machines or something like that, where it basically showed that within the weights of a language model, there is neural programs that it learned from text, and those neural programs can basically transfer to a bunch of weird things, right? Like matching sinusoids, I forget what the other things were, but like basically there's a ton of intelligence in here. And even though it seems like there shouldn't be, right? Like what is this VLM? What has it been trained on? It's been trained on like question answering, right? Like how many, what breed of dog is this, right? Like how many peacocks are in this image? Like, draw a bounding box, right? Like it doesn't feel like there should be any transfer between that and controlling a humanoid robot, but there is, right? And that's kind of that's what I mean by the magic, is that there's some weird intelligence inside an LLM that you're getting. So imagine this paper, right? But replace this little MLP or feed-forward network with O3, right? And everything is exactly the same. You're just pushing a little bit of gradients into it. Maybe you're kind of freezing part of it so that you're not really pushing too much, but I think that's where this is headed. And that actually kind of ends up looking a lot like that guy asked earlier, where he's like, one policy is used for everything. Yeah, I mean, that's going to be kind of the case, right? Where like the model that's running in the robot will end up being kind of basically the same model that you're using to chat and do deep research, except it's received a little bit of extra gradients to get it to do this kind of humanoid stuff. But it's like largely the intelligence is there from kind of the text-based tasks or the VLM kind of like vision-based tasks that it's been doing before. I don't know if that makes sense. There's a lot of unutilized intelligence from the VLM when used in this application, a lot of wasted parameter space and therefore compute. Yeah, and that's actually why, like, why do these guys use these little feed-forward networks and these MLPs? It's because a little tiny MLP or feed-forward network like this is extremely fast, right? You can have 100 hertz control loop running on this, right? You can't do 100 hertz control loop with a VLM, right? The VLMs, even if you make them very small, you're at like the 10 hertz kind of control loop, right? So right now, people are kind of doing both of them, right? Well, where they'll have a VLM kind of operating at the 10 hertz, and then they'll have like these lower level MLPs that are operating at the 100 hertz, right? But I think eventually there's so much pressure to make these VLMs, right, or LLMs work very well on hardware, right? Like there's think about all the money that is going into getting a high tokens per second on your cell phone, right? All the engineering and the kind of benefits of that are also going to make it so that running like getting tokens per second on a robot hardware is going to also benefit from that. So right now you're using these MLPs because they're fast, but I think you give it another 2 or 3 years, and even like a 7B model, even though it's producing all these tokens, it's still going to be fast enough that you can run 100 hertz control and then control a humanoid. I am portraying a crazy hyper-humanoid world in the future. Yeah, I mean, the humanoid robot, like people aren't stupid, right? Like people aren't dumping millions and millions and millions of dollars into humanoids because it's a stupid idea. It's a very good idea, right? Like just beyond the fact that humanoids can kind of do a very wide amount of tasks compared to specialized robots, I think there's just almost like a love kind of situation where it's like more than any other form factor, the humanoid form factor just like hits humans in the right way, right? There's a reason C3PO is a humanoid, right? And even though we can kind of, actually, this is an amazing transition, but okay, yeah, let's use this as a transition, right? Because there was one other paper that I wanted to talk about today, and that was this paper, Elegant, Expressive and Functional Movement Design for Non-Anthropomorphic Robots, right? So I was kind of laying the case there for the humanoid robots, right? Where there's just like something about the humanoid form that just scratches humans in the right place and is a huge reason why I feel like humanoids are going to be very dominant in the world of robotics. But there's also a good case to be made for kind of the more R2-D2 kind of situation, right? Where there's not R2-D2 compared to C3PO. R2-D2 is actually the more loved character, right? And part of that is this kind of what they call expressive movement design. So in this paper by Apple, they basically have this very cute little like kind of like Pixar lamp that it kind of like, let's see if we actually go to the videos. I think they have very nice videos for these. Let's just control, copy, paste that in there. No. Apple Robotics paper lamp. Here we go. Let's click on this first link. There you go. You see how cute this little lamp is? It bounces with you, and it does like really cute little things, and right? And they kind of make this fancy plot about it, but like, for example, if you wanted to like pick up an object, like there's some trajectory in the space of robot actions that is kind of going directly to that object, but then there's a different trajectory that is less optimal, but has this kind of notion of expressionness, right? Where like, rather than kind of moving directly to the object, I'm going to kind of like bounce around before I hit the object so that it like kind of looks a little bit more human, right? Where like the whole point here is to kind of have emotion and attitude in the robot, where a robot might use light, bouncy movements to convey happiness, slow movements to suggest a relaxed state, and lower its head to indicate sadness, or employ sudden jerky motions to signal fear or other negative emotions, right? And even C3PO does this, right? When you think about C3PO, whenever C3PO is like startled, he kind of like jumps, right? But that doesn't make any sense because C3PO is like a robot, right? So like, why does C3PO have like a surprise response, right? Like animals have surprise responses. If you like scare a cat, it kind of like jumps up and like gets tense, that there's no reason for a robot to do that if it's surprised, but you put that in there so that it tricks you into thinking that it's also a mammal, right? Because humans, being mammals, we kind of want that. We fall in love with things that are closer to us in this kind of space of all possible morphologies, right? Here's a space of possible morphologies. You have zoomorphic, appliance-like, and anthropomorphic. And then this little lamp is somewhere right here. But here's another crazy thing to think about is this is going to get gamed as well, right? So the same way that you can kind of use human data sets to kind of like create robot motion, right? So like imagine if you were trying to create this like jump shot model just from pure reinforcement learning, right? Imagine how much reinforcement learning you would have to do before the robots like do a jump shot and then end up realizing that that's the best way to shoot a basketball, and then they end up doing jump shot, right? Like they basically have to independently discover jump shots. That's significantly harder than something like this, where you're basically bootstrapping from the fact that humans have already discovered what a very optimal jump shot looks like. So you kind of start from that, and then you're mostly just doing RL just to kind of like close the sim to real gap, but you're not doing RL to discover the jump shot, right? So there's probably going to be like a similar kind of thing with this, where there's going to be motions that human do that increase the kind of like emotional response, and then we're going to use that to bootstrap and then do RL on top of that to make it even more emotionally attracting, right? The same way that like social media algorithms became more and more addictive, kind of by, they're not doing RL explicitly, but they're kind of doing a type of RL where they're interacting with an environment. They get some kind of signal or reward feedback from that environment, and they're using that to update the system or the policy that actually executes the thing, right? So a similar kind of thing is going to happen here, where the robots that are kind of more enticing are going to get sold more, and then the companies that make those are going to put algorithms on these robots that kind of try to get you to fall in love with these robots, right? And they're going to be really good at that, right? Like, it's going to be weird, but you're probably going to see like humanoid robots that kind of like bounce around like those little anime characters, you know, because it just makes them more cute. As a compute and observability hardware improves and further optimizations keep increasing, the degrees of freedom will exceed our own. Maybe, yeah, I could see. I think for humanoid robots, there's that strong kind of like forcing function of the human form. So even though, for example, having more fingers could probably help you be more better at manipulating, I think we'll converge towards a humanoid form factor that looks very, very human. But yeah, in terms of like these type of robots, right, as individual motors get cheaper and compute gets cheaper, which means you can have larger action spaces, yeah, I think we could see a world where your average robot has way more than 6 joints. I've actually been working on a light and cheap quadruped. This is Elliot. It's why I've been looking into Real2Sim2Real. Difficult matching that with a typical analog control scheme, though. Yeah, a lot of the quadrupeds right now, like, you can basically do RL from scratch. So, like, if you have one of these quadrupeds in Sim, you can get it to stand up and walk just basically from scratch. But it's not very sample efficient, and the walking policies that you get from that are like a little bit weird sometimes. You know, they're like asymmetric, and the robot's kind of like hopping in like a weird way. So there's probably there's a paper there, right? You can imagine a paper that's basically this exact same thing, but for quadrupeds, where basically you start from like dog videos and cheetah videos and, you know, all kinds of quadruped videos, and then use them. There's no such thing as simple for dogs. I don't know. Is there pose tracking for dogs? Pose tracking for quadrupeds? Yeah, there is. Look at that. Dog pose estimation. Pretty good. But yeah, you can, like, evolution already went through the process of figuring out what the most efficient quadruped gaits are, right? And we have a lot of examples of very efficient and very good quadruped gaits. We have things like cheetahs, right? Elephants. The way that elephants walk is they actually kind of heel toe walk, similar to how humans walk. So it's a very energy efficient style of walking. So yeah, you could probably do something similar for quadrupeds, where you basically do this real to sim and then back to real. There are papers out there doing this exact same paper. Yeah, I mean, that's also part of it too. Like, whenever you guys watch these streams, it's like I'm doing some amount of curation in terms of like picking the papers that I think are more interesting, but we've gotten to the point of like machine learning and AI like papers that there's literally hundreds of these papers that get published. So, you know, I don't know, like, I'm only sampling a small subset of the papers. So for every single one of these papers, there's probably like 4 other papers that like do the exact same thing that like I didn't know about. And it's not like I looked at all 4 of them and I said, this one is the best, and that's why I'm picking this one. It's just like, this is the one that the internet and algorithm decided to feed to me. And, you know, sure, there's some amount of kind of selection bias there where like, the same paper coming out of MIT is probably going to get more reads than the same paper coming out of some random lab that hasn't been heard of. And maybe the other lab that nobody heard of, the paper's even better. So I'm actually reading a shittier version of this paper than I could be if I found the other paper. But, I have a limited amount of time. So I'm just kind of picking the papers that the algorithm feeds me. Okay, is there anything else I wanted to say? I feel like I got most of it done. This is the PyNot policy. This is pretty good. Like the open sourcing PyNot from Physical Intelligence, I highly approve of this. I think there's a lot of industrial tasks that can transfer from this, right? Like they did it across a variety of robots. So like you're not going to be able to deploy this on a humanoid and get anywhere, but like, there's a lot of people working on these like arms, and I feel like that's probably the best model to use right now, right? You could also deploy it there. Gaussian mesh hybrids. I think this will go away. I think eventually it'll just be all Gaussians and then Gaussian-based physics. But Real2Sim2Real is here to stay. Right, and like, what does this look like end state, right? Like, what does it look like when you actually get a humanoid in your house, right? Well, actually, the first thing that the humanoid is going to do is it's going to walk around your house and then map the entire house. And then once it creates this map of your house, it's going to then basically sit there and in simulation train picking up things in your house and moving over here and then grabbing this and flipping all your light switches. So like, this Real2Sim2Real is probably going to occur at like this kind of almost like micro level where it's like any robot that's deployed in an environment is going to create a simulated version of that real world environment, do a bunch of RL in that simulation, and then that's what's actually being deployed on the actual robot, right? Versus I feel like a lot of people, the way they see this going is that there's going to be one model that's trained in simulation as well, but then once you go to your house, it's done. It's never receiving any more gradients. It's never doing anything. It's just kind of zero-shotting to your house. But I feel like the way that I see this going, I think it's actually going to do a little bit of extra RL for your house specifically, right? So like there's going to be a little bit of this online RL and environment, right? Versus a lot of people think that there'd be no reason to have to do that for your house specifically, but I feel like it's just going to be easy. So why not? Why not create a little virtual version of your house and then the robot does a bunch of RL inside your fake house? Do note their 4x replay speed. Yeah, I mean, that's standard. 5x speed. 4x speed. Dude, imagine being there in person with 4x speed and it's like moving in this like super jerky way. Jesus. In context learning like we get in LLMs. Yeah, it's kind of like, I think so I mean, like in context learning is basically like you put examples in the context, right? So this is the context right here, right? So like rather than feeding this vision language model just the tokens that represent this image and then the actual command, imagine if you had like 10 examples of this and you literally put it in the context, right? So if we have models with a very large context length, then you can do a lot of in-context learning. But the problem is that putting stuff in the context, you're basically fundamentally limited by the hardware, right? Like what is the actual memory that you have available on the actual device where you're running this, right? So if we're doing kind of more in-context learning, then to me, that's a world where the model is not even running on the robot, the model is running in the cloud. And that's possible, right? You can imagine a world where like satellite internet gets very, very good, the latency basically gets solved, and now you can actually have a model that's running on the cloud that's outputting actions to your robot, right? So like, I think right now the assumption is that the model's going to run on the edge, right? It's going to actually run on the robot, but that's because the latency of like actually having something in the cloud run your robot in your house is too much. But I could see there's various ways that the technology tree could end up in a place where your robot is actually dumb and has no GPU on it, and it's basically just using the cloud GPUs. And if you're going to use a cloud GPU, right, that cloud GPU has so much memory that, yeah, you can do in-context learning and put 10 books in the context, right, because there's so much memory on that. But if we end up in a world where the model is running on the edge, it's actually running on your robot, I think there's going to be so much constraints there, because you really need it to run quickly, that having this huge context is going to be difficult. So you might not be able to do in-context learning if we're running things on the edge. So the delta can also be seen as a glue on top of the glue concept with VLMs. So when I talk about the glue concept of a VLM, what I'm talking about is that the image encoder is not producing tokens that a language model can read, right? Or can consume. So when you train a VLM, what you're really doing is you're training an LLM, and then you're training a image encoder, and then you're gluing them together with usually like a little tiny layer, like a little tiny, sometimes called projector or adapter. That's what I'm calling with the glue. The delta action model, where is it? Right here. In this case, the delta action model is it's a model that's consuming the action and the state, and it's outputting a little delta on the action. So in the case of this robot humanoid, the action is basically 23 numbers that represent the joints, right? So a number for each of these joints. So it's not quite the same thing, right? Because in the VLM, the glue is kind of like taking that feature that's coming out of the encoder and turning it into these like tokens. In this one, it's taking in that action and then giving you some kind of delta action that you can then add to the action and then feed that into the simulator, so that it makes the real world and the simulator more similar. What if we added small per actuator networks? They'd predict and compensate for real world actuator imperfections and fastest. Yeah, I like that idea too, D. Wally God. That's something that I've thought about before as well, where you already have a little PID controller, right? So like if you actually went all the way to the closest you can to the metal, right? Jesus Christ, this paper takes so long to load. But there's this little, where is it? Right here. There's a little PID controller with these values, KPI and KDI, and you can also have the I in there, right? PD is like a simpler version of PID. It just gets rid of that I. But those numbers are just like random numbers that someone picked, right? They tuned them. But I could imagine a world where you replace this entire kind of control stack that's right at the at the hardware level. What if you get to the point where you can replace that with a little tiny neural net, right? A little tiny neural net that's actually the output of that little tiny neural net is literally how much current, right? How much electricity you're actually using on that motor, right? So like, we're only using deep learning up until the point where here's the joint angle that I want, and then we're using all this kind of classic PID control to actually figure out what the current is that we're going to output at that joint. So if Karpathy is right, and the neural net kind of eats every piece of the software, right, and you end up having full end-to-end, right, that means you go end-to-end all the way, right? You don't go end-to-end to the PID controller, and then you have a little PID controller. You go end-to-end all the way to the end, which is the actual, like, motor current, right? So, yeah, I can imagine a world where the motors that you buy have a little chip in there with a little hard-coded little neural net. Maybe it's not even hard-coded. Maybe it can be tuned ever so slightly. So you're basically replacing that very kind of end PID with a little neural net. And then whenever you're doing sim-to-real transfer or sim-to-real kind of stuff like this delta action, like, that's what you're changing, right? You're changing the delta action model is literally that at the very end there. I can't imagine cloud GPU compute for actions would ever be feasible given the latencies. Yeah, I mean, right now you definitely couldn't do it. But like I said, imagine like a couple more generations of satellite internet. Imagine, maybe with quantum computers, we come up with some kind of crazy like quantum tunneling kind of situation, because with quantum stuff, right, there's a way to like almost pass information instantaneously between two things, right? So there could be some kind of like faster than light type of information communication that we figure out with quantum computers. And then once you do that, right, like why do you have to have your compute on the actual robot, right? The robot could be operating in Mars, but the actual GPU is on the Earth, which is crazy to think about, right? But that's the way technology works. Is like when you're trying to predict how technology evolves, it's like you can't just extrapolate from what we have right now, right? That's like the problem with humans, is that we think kind of linearly, right? We basically take what we have and we extrapolate, and that's how we predict the future. But if you try to do that, you can't actually end up predicting the future, right? If you were sitting there in 2018 and you just extrapolated from what we have, you would have not predicted like the LLM craze, right? And the ChatGPT moment and like test time compute. So it's like you have to basically account for these kind of black swan kind of like step function improvements in the technology. So when I'm talking about like this kind of idea of the actual model that's running your robot, not even running on the robot and running in some kind of data center, I'm accounting for the fact that there's going to be a couple upgrades that I could not predict right now that could allow that to happen. Current controller based on a neural net. Yeah, that's full edge to edge, full end to end, you know, like people say end to end right now, but it's not really end to end, you know, because think about all the compute that is happening from the time that photon hits that camera sensor. There's like a bunch of hard coded compute before it actually ends up going into your model. And then it goes through your policy, through your model. And then there's a bunch of other hard coded compute, this little PID, and then a couple more things before it actually finally turns into electricity that goes into your motor, right? So like, even though we call it end-to-end robotics or an end-to-end model, there's still hard-coded compute on both sides, right? So like, I think that eventually that stuff goes away as well, right? It's like, it's basically keeps going all the way to the edge, right? And you can imagine like a neural net in the future that is like literally the input is like the actual like photon counts that are coming from each of the little tiny sensors in that camera thing. All right. Anything else, guys? Let me scroll up a little bit, see if I can find any questions that I missed. Did I see the paper where they used a graph transformer network in RL? Yeah, graph networks are there was like a point where they were popular, but I don't know. I'm just not. I feel like they're just kind of niche, and they're going to kind of stay niche. But slow cheeseburger, okay. Asynchronous, no worries. Okay, the feed performed. Was that Toyota's basketball robot? Yeah, Toyota had this basketball robot, but it was barely doing a jump shot. You know what I'm saying? It's kind of like hard. It's like fixed in this position, and it just goes like this, and it's almost more of like a catapult than an actual robot. It's like a carefully tuned catapult. I don't even know how they trained it. I doubt they used like deep learning. It's probably just all classic robotics, kind of like physics-based control. Can you explain? I think I already answered that. Okay. That's pretty much it, guys. Thanks for covering our transhumanist evolution. We're already not humans. Like, you just have to realize that, like, go anywhere in public and just look at everyone and like they're just sitting there on their phones. Like we're barely human, you know, like the difference between us and like, you know, like even just like 100 years ago, like 100 years ago, you could look at those people and say they were still living a pretty human life. But you look at us right now, I feel like we're barely living a human life. So not that that's a bad thing, you know, it's just different. All right, guys, that's pretty much it. That's Real2Sim2Real. You can write it like this, or you can write it like a cool kid. So this is how the cool kids write it. All right, guys, that's pretty much it. I'm going to stop there. Sorry about the interrupt. Thanks for watching. Thanks, Elliot, Sarah, Diwali, Majetti, SHZ, Casey, Elliot, Sarah, Snooks. Who else? Pratik, Brandon, Srinivas. Oh, Srinivas had a question here. What is the reward which is being used to reduce the gap between the state in sim versus state in hardware? Let's answer that. So to train the delta action model, so you're talking about this process here, where they're training this delta action model. The reward that is being used to push a gradient into the delta action model is this right here. It's the difference between the actual state that the simulator outputs. So if you take this delta action in the simulator, it's going to produce some next state, and then you say, okay, well, how similar is that state to the state that I actually got in the reference action? That's how you train this delta action model. Okay. Thanks, Swati B, Ario, Brandon, Casey, Ed, Timothy, Sagar, Lil KM, and Mark B. Thanks, everybody, and see you guys next week.